All right, today we're going to continue with our circuits, and we're going to get into series and parallel resistors, and that's just ways of combining things on a circuit. Before we get to those, though, let's go ahead and talk quickly about switches. They're pretty basic. So we've got our voltage source here. Remember the two lines, the longer one's positive, the shorter one is negative. Here's our switch. That's what a switch looks like. Here's our resistor and just some wires to finish up so we have current. Now this is a switch. A switch we say is open or closed, if I can spell correctly. In other words, it turns off if it's open, meaning that the circuit is open, there's no way for the electricity to flow. Or if we close the switch, then it is on, turns on. If it's open, it's also stopped. You can think of it as being that it stops the current. And if you close it, it starts the current. And there's a couple of different types of switches. The main ones that we might see this year would be a push button switch. So we would have our two pieces of metal here. We would push down. Sorry, I'll put that in the screen. Push down on that, and that metal then would connect those two plates. We could also have another common one as a slide switch. Again, you have your two pieces of metal for your circuit, and you just have another piece of metal that you would just slide over to close that, or you slide it back the other way to open the circuit. So when we have multiple things that we want to run electricity through, multiple things for us to power, one way to do them is in series. And in series, it just means that you have them one after the other. So we have one thing, second thing, third thing, and they're just in order. Now, a circuit doesn't have to flow in a straight line. It can bend. So it might look like this. This is another way to do three things and get back to your voltage source. Because remember, we got to close that circuit. We've got to have a complete path there. One thing about these, this is like your old-timey Christmas lights, where if one bulb went out, they all go out. So things that are in series are dependent. It's got to go, the electricity's got to go through each one before and make it all the way around back to the voltage source for it to work. So they're dependent on each other to work. Now, if it's parallel, that means it kind of branches off. So you have something that looks like this, where you have two resistors here, but the electricity or the current can split, and it does split and goes in two different paths there. Now, your Christmas lights, some of your new Christmas lights, especially your LEDs and stuff, they're in a line like this, but they also have a second path for that electricity to follow around, so that if this one goes out, then it keeps going. So these would be independent. If one goes out, the others stay on. So that is a good thing. You can have combinations. You can have a switch, which would make things turn on and off. Think about a wall switch that controls a ceiling fan. And you can have your fan on, you can have your light on, you can have both on, or you can have both off. They are independent of each other. That's a great example of parallel circuits. So when we get into the math, one of these is really easy. The series is really easy. The other one is a little more complicated, but not too bad. The effective resistance of resistors in parallel, so things that we're just going to have in order, is R1 plus R2 plus R3, dot, dot, dot. So as many of them that you have in order, you just add them up, and you're good to go. So consider a circuit with 15 ohm resistor and a 12 ohm resistor in series. Determine the effective resistance. Well, if we drew a quick little diagram, you don't have to do this. I'm a visual person. I like to draw a picture of things. So we have 15 ohms here, 12 ohms here. Our effective resistance would be adding them up. So 15 plus 12 gives us 27 ohms. One thing to note here is that the effective resistance of something in series, the effective resistance is always going to be greater than any individual resistor because we're always adding them on. So even if you add something small, it's going to be greater than what you start with. Also, if we look at Ohm's law, V equals IR, typically V is set because you're working, depends on where you are. If you're working in a house, it's 120 volts. If it's on a car, it's 12 volts. If we're dealing with batteries, say in a remote, and you've got two AA's, that's going to be 1.5 times 2, which is 3. So we're working with 3 volts. So typically this is set, and you just control the current by controlling the resistance. So if we have the resistance go up, which is what happens in a series circuit, and V is set, if resistance goes up, then current must go down. So as we add things on in series, where the current keeps going down, down, down. So if we add too many things in a series, we don't have enough current to then work each of the individual objects. So we have to be careful with that. So that's why you don't want to ever link a surge protector into an extension cord into another surge protector and to do a chain like that. You just start lowering the current. Also with a surge protector, we can talk about parallel, and what happens there is a little bit different as well. So the formula for this is the reciprocal of the effective resistance is the sum of the reciprocals of each individual resistor. Now that sounds strange. Formula looks strange, but it's actually not too bad to type into your calculator. I'm going to show you that on this next thing here. The effective resistance of things in parallel here is less than any individual resistor. So if we've got 10, 20, 40, and at the very end we add a 1 resistor, then the sum is going to be less than 1. It's going to be less than our smallest resistor, which is interesting math. Again, if we look at Ohm's law, we have V equals IR. V is typically set. This, putting things in parallel, lowers the resistance, which then raises the current. If we raise the current, that could be dangerous, right? If we put enough things in parallel and the current gets too high, we start burning out circuits. That's not good. So we got to be very careful when we start putting things in parallel. So when you replace your wall socket from the 2 plugs that it had to a 6-plug extension, you got to be very careful, right? That's 3 times the amount of things that can be plugged in there. So let's draw, we got the same 2 resistors, let's draw them in parallel this time. Let's make sure that's longer. So I'm going to draw them in parallel like this. Lots of different ways you can configure this. Here's our 15 ohm resistor and our 12 ohm resistor. So our equation would look like this. It's kind of crazy, scary. I would type it into your calculator a little bit differently. I would do 15 to the negative 1 plus 12 to the negative 1 all to the negative 1. This negative 1 can be found on your graphing calculator as this button on the left side. So you have a button that has x to the negative 1, so you can just type in the resistor, type in the reciprocal button, plus 12, the reciprocal button, close your parentheses, reciprocal, and you've got your answer. Be careful, sometimes people forget to do this last reciprocal and they just give me this, which turns out to be a really, really small number usually, and that is not the answer, so just be careful. It is going to be less than 12 and 15, but you still need it to be the right size. So moving on, we've got the difference between a fuse and a circuit breaker. Both of these do the same thing. They both protect the circuit components. So, like we said, when we put things in parallel, the current goes up. If it gets too high, we start burning out wires and things like that. Well, a lot of circuits can be very expensive. A lot of electronics can be very expensive. So we want something to protect these electronics, these circuits that we have. And so we have these two things. First one is a fuse. This is a one-time cheap use item. What happens is as the current increases, it actually melts the metal in the fuse and it breaks open the circuit, stopping electricity flowing. And so if this happens, you just have to replace the fuse and you're good to go. Circuit breaker, on the other hand, is slightly different. It does the same thing. It's going to break open the circuit breaker. But these are the ones that are on your house, and you might have blown or popped the breaker. So you have to go into your circuit breaker box and reset it. And when you reset it, it's clear that it's a multi-use. You can pop it several times before it quits working on you, and it's like it bends when you got two pieces of metal and you heat them up. One typically is going to expand faster than the other. So think of it like Pop-Tarts, iced Pop-Tarts. When you toast those Pop-Tarts, the cake part and the icing part expand at different rates. And so the icing part makes it bend, and you've got a bent Pop-Tart, right? That's what happens when you heat up this metal. One part expands more quickly, therefore bending and pushing the circuit breaker open. So this bends to open the circuit. So once it cools off, you can reset it, and it's closed and ready to go again. So let's look at an example of this. We're going to combine these two ideas here. An electrician is making a circuit with a 12-volt electric potential. So we're working on a car. 9 ohms, 15 ohms, 8 ohm resistors in parallel. She needs to decide how big a fuse to put on the circuit so she can draw enough current to function, but not so much current that it will overheat. She has fuses rated for 2, 4, and 6 amps. Notice this is comparing to the current. So we need to figure out what the current is. Well, V equals IR. So I equals V divided by R. Well, we have the voltage. That's 12. That's easy. They gave that to us. We need the effective resistance. Well, that's 1 over each of the resistors added together. So practice that on your calculator, but you should come out to 3.3 ohms. You plug that in here because we're not looking for the effective resistance. We're looking for how much current is all three of those going to pull. Well, it comes out to be 3.6. Now, it's not always going to be so close. It just happens to be close in this case. So if we look, we have a 2 amp fuse, a 4 amp fuse, and 6 amps fuse to use. You can't use a 2 amp fuse because if all three are going, then 3.6 amps would pop that every single time. 4 amp is pretty good. There is going to be some variance, so we don't necessarily want it to like be 3.7 or anything like that. That's pretty close. But if we go all the way up to 6, that's almost double what we have here, so we definitely don't want that. So I would go with the 4 amp, and if we have any trouble, we'd have to research, maybe reconfigure something from there.